Boldly going where no science show has gone before. The Naked Scientists.
Hello and welcome to this week's Naked Scientists with me, Chris Smith, and also with Kat Arney. Hello, Kat.
Hello.
Now, coming up, why recessions are good for your health. At least you're probably less likely to die during one, and we'll find out why in a minute. Also, they say that you lose at least one brain cell every single second. And now scientists have uncovered the genetic switch that determines how many neurons you actually make in the first place. So I guess we can find out who's in trouble in the future, if nothing else. And also, an ultrasound scan for the planet. Scientists have discovered how to use the Earth's natural vibrations to build up a three-dimensional picture of what lies hundreds of kilometres underneath our feet. And we'll find out how it works in just a minute. Kat.
I'm at the National Cancer Research Institute's annual conference in Birmingham to bring you all the latest news on cancer. We'll be hearing how directed beams of charged particles can target individual cancer cells, Mira discovers the role of stem cells in breast cancer, and I'll be finding out about the latest advances in hormone-blocking cancer drugs.
And in kitchen science, Ben and Dave are finding out what they can see in sounds like these. And believe it or not, that's the sound of Dave clapping after it's been slowed down. You can find out why they're recording claps in a dark room and what they can tell us about medical imaging in just a moment. That's all coming up on this week's Naked Scientists. If you'd like to join in, do drop us a line, chris@thenakedscientist.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
So that's all excitingly on the way, but before then, to a legacy of 1900 or thereabouts, the world's most popular painkiller, and something that came shortly after it, Kat, the world's perhaps most unpopular infection, certainly at the moment, the flu. What can you tell us about this?
Yes, those little white pills of aspirin have been popped by millions of people since the drug came onto the market back in 1899, and today around 40,000 tonnes of aspirin are sold every year around the world. But a new paper published in the journal Clinical Infectious Diseases suggests that misuse of aspirin to relieve the symptoms of flu could actually do more harm than good, at least in the case of the 1918 flu pandemic.
So rather worrying, given how many people actually take aspirin. It's a very popular drug. Current fears over H1N1 are still out there, of course. What's the story here?
Well, this is work from Karen Starko in California, and she thinks that very high doses of aspirin that were given to some patients during the flu pandemic in 1918 and 1919, I mean, we're talking big doses, up to 30 grams a day, might have caused dangerous side effects such as a build-up of fluid in the lungs. Now, in turn, this would contribute to the deadly effects of the flu and increase the chances of lung infections. Now, we do know that doses this high can cause these kind of side effects, and we see this in people who have aspirin poisoning. And adding to this evidence, the US Surgeon General recommended the use of aspirin for flu just before a massive spike in flu deaths back in 1918.
Indeed, and to put that in perspective, you can take 1 gram of aspirin every 4 hours or so. So that's 6 grams per day maximum you should take. This is a dose, of course, perhaps 5 times higher than that. So how many people would have been affected by this misadvice?
Well, based on what we know about the percentage of people who get fluid in their lungs when they take really high doses of aspirin, this could have affected up to about 1 in 30 people treated with aspirin. And when you add up how many thousands of people died from the flu at that time, that's quite a significant number that might have actually died due to aspirin. And what's more, Starko thinks that this unusually high number of deaths was seen in young people. So maybe these young people who normally fight off the flu, some of their deaths might have been due to aspirin use, maybe rather than the flu.
And so what does this mean actually today in contemporary terms, as we're sort of sitting here in the Northern Hemisphere waiting for the flu season to come back and potentially a resurgence of H1N1 swine flu?
Well, hopefully we're more sensible than taking 30 grams of aspirin a day. And back in the early 20th century, aspirin was such a new drug, doctors didn't really know how to use it. They thought maybe more was better. And it was also very pushed by pharmaceutical companies because the doctors didn't really have anything to do. So they just thought, well, we'll give people this drug, hopefully it might work. Today we do know much more about aspirin and some of the really complex ways it affects the body. But we do need to take this as a warning from history not to get carried away with super high doses of drugs.
Indeed. So there's everything to play for, though. We're hopefully in a better position than we were about 100 years ago. Well, look, sticking with history and also things that might kill you, the Conservative Health Minister, Shadow Health Secretary Andrew Lansley, got himself in a bit of hot water earlier this year when he said don't worry, Britain might be facing the worst credit crisis we've had in years, but recessions are actually good for your health. And people shot him down for it and said, it's a very naughty thing to say, you shouldn't have come out with that. But the reality is that there is evidence that science supports the statement. Having a recession does appear to be good for you, believe it or not. There's a paper actually in the journal PNAS this week that examines this in slightly more detail and confirms the suggestion that recessions are good for your health. This is Jose Tapia Granados and Ana Diaz-Roux. She's both at the University of Michigan. And what they've done is look at the US Great Depression. This was a very, very severe financial crash which happened in the 1930s. The Wall Street Stock Exchange collapsed. People lost a fortune. At one time, about 1 person in 2 in some places had no job in America, and the average unemployment rate was running at about 25%. So a very severe crash. One would therefore expect that people are going to be pretty depressed around that time, and therefore if we're going to see peaks in mortality, it's going to be around then. Well, they said, let's examine the figures. Let's go back to 1920, look at what the economy is doing, and pair that with mortality data. So they went back to 1920 and they looked at how the economy was doing in 1923, 1926, 1929, and then 1936 to 1937. Those are all years when there was a big financial boom. The economy surged, people made a lot of money. But if you look at those dates, you find that the mortality rate, the overall number of people dying in the population, was actually a lot higher on those years. It peaked in the years when the economy was doing really well. Then you say, well, when were the depressions? When was the economy in recession? Well, in 1921 there was a recession. In 1930 to 1933 there was a recession. And in 1938 there was a recession. And what do you think happened to the mortality rate? Well, at exactly those dates, it was at its all-time low. So although there was a general trend of improve living conditions over this time, whenever the recession was in or the economy was doing really badly, people actually lived longer.
So tell me, Chris, how does this actually work? How can a recession affect your health? What's going on?
Well, some people have suggested that this could be a lag effect. In other words, you get sick during the depression, and then it takes a few years for you to die. And therefore, it's not till the economy is doing really well again that then there's the effect of the previous recession, and then lots of people die. This can't be right, though, the researchers argue, because the dates just don't add up, for a start, because there are variable distances in time between when there was a boom and a bust, and then when there was the number of people either living longer or living less long. It just doesn't fit statistically. And the other point is that, and this is the one that they say is much more likely to be the case, when we're in a boom and the economy is doing very well, actually there's a lot less that's good for you going on. People have more money to spend on alcohol and cigarettes, so the consumption of things that are bad for your health goes up. Also, when industry is booming, there's more pollution around, there's more traffic on the roads, there are more industrial accidents, there's more migration. People get paid a lucrative amount of money to jet off somewhere else, leave their family behind, so they get very socially isolated, and this in turn has an impact on health. And so it looks like, actually paradoxically, when we're in recession, in fact, people do live longer.
Crazy. I'll be really interested to see the effects of this current recession, because for me it's miserable. Anyway, moving on to a story about the brain. Now, wouldn't it be absolutely fantastic if we could just flick a genetic switch and increase the number of brain cells we have? I would love that. But it would be bad news if this production line ran out of control, because then you would end up with a brain tumour. And now researchers in the US have tracked down the gene responsible for maintaining this tricky balance, making sure we grow enough new nerve cells, but not so many that things get out of hand.
Which sounds really cool. We actually have quite a lot of individuals who have quite a lot of brain cells on their own. They do quite well at making them. So what do these genes actually do?
Well, this is research from William Snyder at the University of North Carolina. Now, he and his team discovered that a gene called GSK3 controls the signals that determine how many nerve cells we have in our brain. Now, GSK3 is a kinase. This is an enzyme. It sticks little molecular tags onto other proteins, switching them on or off to send signals in the cell. And the team have just published their results in the journal Nature Neuroscience.
So how do they find this sort of brain cell on switch?
Well, the researchers used genetic engineering to create mice whose GSK3 gene could be removed at a very specific time during the development of the mouse embryo. Now, this was at a time when a type of brain cell called a radial progenitor is just being made, and these stem cells produce the bulk of the nerve cells in the brain. And the researchers found that removing GSK3 at this crucial time meant that the progenitor cells were kind of locked into a pattern of constant proliferation. They were churning out endless new stem cells rather rather than these becoming mature neurons.
So if you take away this GSK3, that means you end up with, too many immature brain cells. So how can you turn those into an abundance of mature neurons, nerve cells?
Well, that's the next step the researchers are really keen to take. They want to find out if adding this GSK3 back into the brain after a big burst of proliferation will make these new stem cells mature. They think if they can get this to work, they could make mice with 3 to 4 times as many neurons as normal mice. So maybe by manipulating GSK3 levels one day, we could increase our brain capacity. Snyder describes it as dialing up or down the number of neurons that are generated in the brain. But the other potentially important thing is that GSK3 has also recently been fingered for a role in a number of psychiatric illnesses, including schizophrenia, depression and bipolar disorder. And lithium, a common treatment for bipolar disorder, works by shutting down GSK3. So crucially, the researchers suggest that perhaps doctors should avoid giving drugs like lithium to younger children whose brains might still be growing, in case it does lead to problems of overgrowth with cells, which could potentially maybe lead to cancer, but obviously this does need more research.
Indeed, what an intriguing finding, though, because, of course, one thing that unites many of these psychiatric conditions is that they don't kick in until later in life. And that would be consistent with the brain making more neurons a long time and then miswiring them in to different parts of the brain, perhaps creating abnormal pathways connecting bits of the brain that perhaps shouldn't be connected. But certainly an interesting finding. Thank you for that, Kat. Now, I mentioned in the beginning that also this week scientists have made a breakthrough when it comes to seeing what lies hidden beneath our feet. And we're not just talking about getting your shovel out and digging into the nearest field. I'm talking about what lies hundreds of kilometres underground, basically the interior anatomy of our planet. And scientists have discovered how to use the Earth's natural hum. Yes, the planet has a hum, because it doesn't know the words. No, I'm just joking. It has a hum because the planet is vibrating. And it's vibrating because various things, such as atmospheric disturbances and also the crashing of big waves and swells in the ocean, cause deformations on the ocean floor, and these vibrate and resonate through the planet. The hum is very, very low frequency, 0.01 hertz. So in other words, to complete one single wave, it takes over 100 seconds, maybe as long as 400 seconds for one of these resonances to go through. And these very long wavelength waves propagate through the planet's interior, and as they go through different structures, they can get changed, and the pattern of those changes, or the effect that the changes have on the propagation of these waves, can be sampled by recording the vibrations from the surface of the Earth, and then it can be used to build up a picture of what's inside the planet. Now, scientists have done this in the past with vibrations from things like earthquakes, but the problem is that with earthquakes are limited to when the earthquake's actually happening. So maybe there's a better way of doing this on the longer term. And 3 scientists, led by Kiwamu Nishida, who's a researcher at the University of Tokyo, have got a paper in Science this week where they've done just that. They've used this natural hum of the Earth, and by taking the recordings from 1986 through to 2003 of background hum from 54 seismic stations, these are just recording stations around the Earth's surface, they have managed to see how these waves can be used to build up a picture of what's inside the Earth. So the principle is very simple. What you do is record the sound waves, and because they're very random, it's very easy to find simple signature sounds that can be followed all around the Earth. You then record them from various places on the Earth's surface, and you use that to build up a picture of what different geological structures lie deep underground, up to distances of about 500 kilometres. So it goes right down deep inside the planet. So an incredible piece of work, really, this. And why this is so valuable, they say, is that there are some planets, like Mars, for example, which you might not be able to measure earthquakes over a period of time, but you could use disturbances in the Martian atmosphere, which are pummeling the surface of the planet, to do the same trick, and this would tell you what's going on inside the planet. So a wonderful piece of work which tells you an enormous amount, not just about our own planet, but perhaps other worlds too. Now, you're listening to The Naked Scientists with Dr. Chris and Dr. Kat, and this week we're devoting the programme all about, or to the subject of cancer. And Kat is at the National Cancer Research Institute's conference in Birmingham, and so, Kat, hopefully you can give us a bit of an update as to what's going to happen at this conference and a bit about the conference itself.
Yes, well, this is a conference that's organised by the National Cancer Research Institute, the NCRI, which is kind of a virtual institute. They're an umbrella that brings together all the funders of cancer research in the UK. So organisations like Cancer Research UK, Leukemia Research, some pharmaceutical companies, basically to make sure that everyone is doing cancer research in a good way, not missing any areas and not duplicating too much work. So it was set up a few years ago to address the fact that, people didn't really know what was going on in other labs. So basically, this is a conference where cancer researchers from all over the UK, from all over the world, get together to talk about the latest results, to discuss, set up collaborations. And not only are scientists here, but there's doctors, nurses, and also patient groups here as well. So it's a really diverse range of people.
Now, every year when you go to the NCRI conference, you come back with some new hot kid on the biological block. So what are the hot topics in cancer research this year?
Well, there's just been a talk this afternoon by a chap called Larry Norton, who's from the Memorial Sloan Kettering Cancer Center in New York, and it was really, really interesting. Basically, when you think about cancer that starts to spread, there's this idea that there's a starting tumour and cancer cells go off around the body and find new places to go, such as the lungs, the liver, and they start new tumours. His idea is that while a cancer is growing, kind of stem cells, spreading cells, they go off, they travel around the body, and then they come back to the original tumour and they start growing there. So this idea of self-seeding. And what he's proposing is that, say you treat this original tumour, you get rid of it with surgery, with radiotherapy, with chemotherapy, there are still these cells out travelling in the body like the prodigal son, and they try to come back, but there's no original tumour there, and you think, well, I shall go somewhere else. And then they go and start growing in the lungs, in the liver, and in the brain.
So by chopping out the cancer, paradoxically, the primary tumour, we could be encouraging the process of spread.
Well, that's basically the idea. And his ideas are really very new. And at the moment, he's only got research in mouse models that might support this. But it's certainly an intriguing idea. And he's got all sorts of ideas for how you might use this to treat cancer. For example, if you could... So basically the idea that the original tumour is acting like a kind of a sponge absorbing back in these cancer cells. So could we make some kind of fake sponge that would then mop up the cells that have started spreading? Can we find out the signals that they're giving out and try and mimic them or block them that might stop cancer cells spreading? And he's designing some possibly quite counterintuitive regimes of different drugs you might give that would actually help to stop this process and treat cancer more effectively. So there's some really exciting work to be done in the future there, I think.
OK, well, Kat, thank you very much. We'll rejoin Kat in just a second to find out a bit more from the NCRI Cancer Conference. Meanwhile, if you have any questions for us here at The Naked Scientist, you can send them in. It's chris@thenakedscientist.com.
Lifting the lab coat on the world's best science. The Naked Scientists.
In a little while, we'll be finding out how scientists are using a brand new technique to blast apart tumours, and we'll also be finding out how you can do your own ultrasound scan at home. Well, not quite, but we'll show you the technique that's used to do it. First of all, though, we'll kick off with a talk to Professor Karen Kirkby, who's at the University of Surrey, and she's developing a way of treating cancer using proton therapy. Now, this is a targeted beam of protons, they're positive charges, and you can aim these at individual cancer cells to get rid of them. Hello, Karen.
Hello.
Great to have you with us on The Naked Scientist. So tell us a bit, first of all, about the problem with cancer that you're trying to tackle. I mean, everyone's heard of cancer, but it's a generic term. What do we actually mean by it?
I think cancer covers a whole range of diseases, and Kat covered it quite nicely earlier on, where she said about the brain cells. Obviously, we'd all like more brain cells, but we don't want them to go mad and form brain tumours. And that's effectively what cancer is where the cells go mad and start to form tumours in parts of the body where you don't want them.
And so, if you could just summarise, what are the current strategies that we use to get rid of cancer before we start talking about your technique? OK,
well, the current strategies, there's surgery, which is very effective, and I think you're looking about 50% of cancer cures are using surgery. Then we've got radiotherapy, which comes in about 40%, and then chemotherapy, which combined with the other two modalities comes in at about 11%.
And your technique?
Our technique is one that's used rarely in the UK. There is a centre in Clatterbridge which uses it to treat eye cancers, but it's becoming very, very widely used in the States and Europe, largely because of advances in medical imaging. You've got to see the tumour before you can use this technique. So it was thought about in the late 40s, but because at that time you couldn't really see the tumour, it wasn't very good to use. It's a very targeted technique, and what it uses is, whereas with X-rays, if you irradiate a tumour with radiotherapy, the damage that's induced by the X-rays is induced around the tumour, so in front and behind it. Whereas if you use protons and heavier ions, you use something called the Bragg peak, and this is the way the ions actually stop. And if you change the energy so that most of the energy is deposited in the tumour and very little in the surrounding tissue, then you can imagine you put most of the damage into the tumour, very little into the tissue in front of it, and practically none into the tissue behind it.
So this is a way basically of minimising side effects, because radiotherapy is very effective. I mean, you're basically giving a beam of radio waves, X-rays, microwaves, whatever people are using, ionising radiation, into the cells. This damages the DNA of the cells and they die. But the problem is that, as you say, it's unfocused and takes down adjacent tissues which are healthy, and this makes side effects. How do you manage to target your therapy so appropriately just into the tumour itself then?
Well, I think it's largely the physics. Physics works for us beautifully because of this Bragg peak. You get a very, very sharp peak. So if you can imagine going in through the tissue, you put a tiny bit of damage into the tissue in front of the tumour, then there's this big peak as the protons deposit their energy, and then beyond the tumour there's practically none.
First of all, can you just explain the proton bit of it? Why is that novel, and how does that work? And where do you get these protons from?
Well, protons, as I say, they've been thought of for cancer treatments since the work was done back in I think they were first proposed in 1946, and some work was done in Berkeley in the States. But the results were a bit unequivocal, largely because they were irradiating a large amount of the body, simply because they didn't know exactly where the tumour was, because they hadn't got the imaging techniques. So the results then weren't particularly good. But now we can find the tumours. We can target the protons at them. If we use MRI imaging, for example, we can target the protons exactly at the tumour. And it's very useful if you've got a tumour very close to a critical structure, such as the spine, because there's not an exit dose. And therefore, you can put all the damage into the tumour and none into the vulnerable tissue beyond it.
When the tumour gets impacted by the beam of protons, what do the protons do to the tumour? Why do they destroy it? Well,
protons work in a very similar way to X-rays, but of course protons being bigger, they're particles coming in rather than electromagnetic radiation. They basically induce double-strand breaks in the DNA. Now, we know those double-strand breaks can be repaired, but they're much more difficult to repair, and therefore you can start to destroy the tumour much more easily than you could with X-rays. It's a bit like throwing cannonballs rather than ping-pong balls at the tumour.
Which is a good thing. The question is, though, that, as you've said yourself, now we have the ability to image tumours really well, and we can see where they are, and you can target your therapy. That's fine, but what's the resolution of the scanning? In other words, if one of the reasons people die with malignancies is not because of the primary tumour usually, it's because of where it's spread to elsewhere in the body. So are you able to use this kind of therapy to pluck off not just the primary tumour, but those spreads, those metastases as well?
It's being done a lot in Japan. There are stories there in the literature of it being treated for small lung tumours and tumours in the liver, and it's been termed the form of atomic scalpels. That in Japan, they're tending to use protons and carbon ions. So the Japanese are further ahead than we would be in the UK at the moment, but they're using combined modalities of treatment, and there are stories of fishermen being taken off fishing boats, taken to hospital, given something like 10 to 15 fractions, and then being flown back to the fishing boat and being completely cured. As I say, these are some of the stories in the literature, and I've seen pictures of liver tumours where the tumour has completely been removed, and, for example, also tumours in the kidney, which would be difficult to treat with conventional radiotherapy simply because of the collateral damage on things like the bowel.
And is it pretty much any kind of tumour, or are there specific kinds of tumour for which this is more appropriate?
In the UK, the feeling is, first of all, is for paediatric tumours because of, for example, if you're treating tumours of the spine in children, if you use conventional radiotherapy, obviously you'll bathe the rest of the body in radiation. You'll bathe things like the lungs and the heart. And obviously in children, you want to minimise the chance of secondary cancers later on in life. So that is one of the particular ones. It's also very useful if you're close to critical structures. It's part of the armoury. It's not going to replace conventional radiotherapy, but it might be useful for cancers that we can't use radiotherapy for at the moment.
Thank you, Karen. We'll leave it there, but do stay with us. That's Professor Karen Kirkby. She's from the University of Surrey, and she's working on charged particle beams for cancer treatment. They use protons, so needless to say, she's very positive about her research.
Laying the facts bare.
I say.
The Naked Scientists.
And now it's time to join Meera Senthilingam, who's gone along to the Cancer Research UK Institute in Cambridge this week to find out how John Stingle and his team are investigating the role of stem cells in breast cancer development. Now, stem cells are known for their ability to regenerate and differentiate to form lots of the cells in our bodies, but as well as this crucial role in our growth and development, it seems that rogue stem cells might be at the heart of cancer formation in many cases, including in breast cancer. So Meera spoke to John about how he's studying this kind of change in the human breast.
The breast has traditionally been considered being composed of two types of cells. We have luminal cells, which are cells that make milk, and an underlying layer of myoepithelial cells, which as their name implies, they're a muscle-like cell, and they're literally a cell that contracts and squeezes the milk out of the mammary gland. There's a hypothesis that the mammary gland is probably more complex than just milk-producing and muscle-like cells. And it's our hypothesis that there's also stem cells present, mother cells present in the mammary gland that can generate both these luminal cells and myoepithelial cells. And it's been basically our research the last number of years now, where we basically try to identify mammary gland stem cells, for trying to figure out what are all the different types of differentiated cells in the breast, and as well, are there cells in between stem cells and the differentiated daughter cells, cells we would call actually progenitor cells.
How are you trying to understand how this pathway between stem cell to differentiated cell varies when somebody gets breast cancer?
The normal mammary gland is under quite a strict control of homeostasis. So, for example, a stem cell would normally divide and produce a new stem cell, and it would also produce more differentiated daughter cells. So cells would have some proliferative capacity, but they're not as potent as a stem cell. We call these cells a progenitor cell. Then these progenitor cells would produce their daughter cells. And this balance between a stem cell producing one new stem cell and a more mature daughter cell, we think is perturbed in cancer, such that in cancer there may be more a shift to, say, producing more stem cells. Basically, we believe that cancer is a disease of cells that have proliferative capacity, either stem cells or cells with stem cell-like properties. And the reason for this is that you have to keep in mind that cancer is a multi-step process. You don't just get a mutation and get cancer. If that was the case, we'd probably all be dead. In fact, you probably need about, say, 5 or 6 mutations to go from a normal cell to a malignant cell. But the body has developed pretty good methods for protecting its DNA. And the probability of getting a mutation, a meaningful mutation in a cell, is actually quite low, analogous to sort of like winning a lottery. So how is a cell supposed to get, say, 5 mutations in a row? It's like trying to win the lottery 5 times in a row. But if you have a cell that has the ability to generate lots and lots of daughter cells, such as a stem cell. So say just by unlucky chance, a stem cell got a mutation. That stem cell can generate 1 million daughter cells. All of them will have that mutation. Now, the probability that a certain daughter cell will get a second mutation is quite low, but the probability that one of those daughter cells out of that whole population will get a second mutation is quite high. And maybe that second mutation is a mutation that reduces DNA repairability. And therefore, the probability of getting a third mutation is not 1 in a million, but say maybe 1 in 100. Basically, if you target cells that have the ability to grow, you increase your chances of getting multiple mutations.
Because whilst the probabilities are quite low, the fact that so many cells are being generated obviously makes that risk higher.
Exactly.
So how are you going about actually researching this?
We get normal breast tissue from the hospital. This is human breast tissue, say reduction mammoplasty specimens. So women who had their breast surgically reduced. We bring it back to the lab, and we basically mince it up, and we incubate it in an enzyme mixture, which basically degrades all the extracellular matrix, but doesn't hurt the cells. And we basically make a single-cell suspension of human breast tissue. We use a machine called a fluorescence-activated cell sorter, and by tagging the cells with fluorescent molecules, we can purify different subfractions of breast cells.
But now, with your team having separated out to find all of these different cells that are present within a breast, how are you then going to go about actually researching the cancer side of it?
So, for example, again, there are many different types of breast cancers. Are they all arising in a common cell type, or are they arising from different types of breast cancer cells? The way how we're going to test that is, say, for example, you have a oncogene, gene X, and you know that gene X is somehow associated with breast cancer, but you don't know how. Well, what we're going to do is we're going to basically purify subfractions of normal human breast cells, and then using specialized viruses, we can actually infect those cells such that they overexpress oncogene X. And then we can examine, okay, does oncogene X, for example, cause stem cells to expand the stem cell population? Or does it cause a more mature progenitor cell to turn into a stem cell? And then we can also, instead of just introducing oncogene X, we can also put oncogene X, Y, and Z, and seeing what type of cell generates what type of tumor.
So having identified the cause of a tumour, like a particular gene that's causing a tumour, you're inserting it into the different types of cells that are made within a breast to see which of those cells that gene actually affects to become cancerous, essentially.
Yeah, exactly. The problem we've had is that there's been a lack of understanding of the normal cellular context in which oncogenes and tumor suppressor genes exert their actions. For example, does oncogene X, does it cause this one population to expand, or does it cause another population to expand, or does it cause one population to generate another population?
So you don't know whether it's causing one cell to just proliferate, or if it's causing one cell to produce something that causes another cell to proliferate, and so on.
Yeah, so we don't understand the underlying mechanisms of what is actually happening. We only see the end stage result. And it's very important to understand the molecular pathways that regulate stem cell behavior, because you want to target these pathways in order to stop tumor growth. Now, it has been demonstrated, and pretty conclusively, that there is such thing as a breast cancer stem cell. The challenge now is to figure out how abundant are these breast cancer stem cells. Are they identical between different types of breast tumors? And they're probably not. And basically, how do we isolate them, and then how do we target them? And that's basically the stage we're at right now.
That was John Stingle, who's from the Cancer Research UK Cambridge Research Institute, and he was talking to Meera Senthilingam to explain how he and his team are investigating the role of stem cells in breast cancer formation and how those cells change their regulation and how that could be targeted as a potential therapy for cancer treatment. You're listening to The Naked Scientists with Chris Smith and with Kat Arney. Kat's live at the NCRI conference in Birmingham, and I'm here in the studio. I've got a couple of emails in. Keith has emailed us and said, loves the show, great programme. Why aren't you broadcast nationally? That's because, Keith, we're broadcast internationally. You can get The Naked Scientists as a podcast, nakedscientist.com/podcast. Also, John has got in touch. He actually is listening in Florida in the USA. He says, your podcast helped me get through my day's work. I hope he's not an air traffic controller. Also, Lisa Timmus says, I'm not aware of any podcasts that are comparable. They're not remotely as interesting. So thank you to those three. Do get in touch. We heard from Mark Bletchley, who says he's following us on Twitter. If you want to Twitter at us, it's at Naked Scientists. Now, Kat, got a quick question for you. Dally Waverider was listening to your news item about GSK3, the gene that makes you have more brain cells, and he says, is it called GSK because it's owned by GlaxoSmithKline?
Nice one. No, it's something kinase. It may be glucose synthetase kinase. I'm not sure. It says so in the paper. I don't know. But no, it's not owned by GSK.
OK. Another quick question for you. John in Rounds has phoned in and said, is it true that vitamin C helps to cure cancer or perhaps even prevent it? And if so, how's that possible?
No, it isn't. This is something that Linus Pauling put around, the idea that you take massive doses of vitamin C and it can stop you getting cancer or treat cancer. And basically there's no scientific evidence that this works. However, about a year or so ago, there was a paper that showed that injections of vitamin C may help some treatment. I can't remember all the details, but we certainly blogged about it on the Cancer Research UK Science blog. But it's important to stress that obviously vitamin C is an antioxidant, and taking high doses of antioxidants, it may well interfere with some kinds of cancer treatment in ways that we don't really know. And again, it's something that we have blogged about, and it's an area that is really quite interesting because people do love to take vitamin pills.
Indeed, there was also a meta-analysis by Goran Bilakovic, who's at the University of Copenhagen in Denmark. I remember this coming out last year, and they looked at many, many thousands of people who'd all been in little trials on giving antioxidant vitamins like vitamin A, vitamin D, vitamin E, vitamin K, selenium, that kind of thing, vitamin C, and compared that with people's outcomes if they didn't take vitamins. And in fact, in many cases, they found that some chronic vitamin treatments actually resulted in people having a higher mortality rate and morbidity rate than people who didn't take any of these supplements. Modest increase in risk, but at the same time, vitamin A and vitamin E did increase the risk. So the chances are, yes, it's based on sound physiological principles trying to take antioxidants, but the outcomes don't necessarily fit the facts at the moment. So needs more work, I guess, is the bottom line, isn't it, Kat?
Absolutely. Anyway, in case you hadn't noticed, October is Breast Cancer Awareness Month across the UK. You've probably seen the explosion of pink in the shops, and I do think it's a real shame that we don't have blue everywhere for men's cancers. I think there's something to be done there, chaps. Come on. Get sorted. Anyway, breast cancer is still the most common cancer in the UK. It affects around 45,000 women and around 300 men every year. And although survival rates are improving year on year, there are thousands of people who still lose their lives to breast cancer. And often this is because hormone-blocking treatments such as tamoxifen or anastrozole stop working after a while. Now, Cancer Research UK's Professor Charles Coombs is a leading breast cancer researcher at Imperial College in London. And I went to find out more about the role of hormones in breast cancer and some of the promising new treatments he and his team are developing.
Hormones, mainly estrogen, drives breast cancer cells to divide. So it acts as a sort of fertilizer for breast cancer cells. And tamoxifen has been the standard way that people have tried to block estrogen action, because tamoxifen is an anti-estrogen. So it prevents estrogen from gaining access to the cells to cause the cells to divide. The problem is that more than half of breast cancers eventually become insensitive to tamoxifen. And so the first drug that we developed was, if you want, a drug that would work after tamoxifen has exerted its action and worked. And that class of drugs are called aromatase inhibitors. And those drugs are drugs such as Arimidex, exemestane, letrozole, those sorts of drugs. They're all inhibitors of estrogen synthesis. Under those circumstances, what happens is that a cancer cell becomes resistant to tamoxifen by overexpressing the estrogen receptor, and the way to make those cancer cells die is to withdraw estrogen completely. If you withdrew estrogen after tamoxifen treatment, you could get a lot of cancer cells to die that had become resistant to tamoxifen.
And that's what these aromatase inhibitors do.
Exactly. So what we've been trying to understand is, why do breast cancer cells become resistant to aromatase inhibitors? This has been the next big challenge. And after about 15 years of work, we now think that we understand the mechanism. What happens is that various other signaling pathways in the breast cancer cell, as it were, impinges on the estrogen receptor. So it increases its sensitivity. So this is a hypersensitized estrogen receptor. Now, aromatase inhibitors, although they stop the body from making estrogen and lower the estrogen very significantly, often by as much as 99%, they don't actually reduce it by 100%. But this low level of persistent estrogen can be amplified. The effect of that can be amplified by various other enzymes, which can be used to target in breast cancer. So one enzyme that we've recently discovered that does this is something called CDK7, and we now, over the last 2 years, have developed a specific inhibitor for CDK7, which prevents the activation of the estrogen receptor. So that drug is now being optimized and will be, we hope, available for women whose cancer cells have become resistant to aromatase inhibitors. Another route that we have gone down, and which has already produced a drug, which is now being tested throughout Europe, is in looking for other sources of this residual tiny percentage of estrogen that remains after aromatase inhibitors have been used. It turns out that breast cancer cells can bypass the aromatase pathway by using a storage form of estrogen.
So it's a bit like having a spare tank of estrogen hidden away.
Exactly, in a storage form called estrogen sulfate. And there's an enzyme called estrogen sulfatase, which cleaves this sulfate off, thus liberating the estrogen. And so it's a very clever way that the breast cancer cells use this enzyme to liberate estrogen, which can then sit on the receptor even when aromatase inhibitors are being used, and then drive the cancer cell to divide.
So how do you try and combat the actions there?
Right, well, it's taken, again, about 15 or 20 years' work, mainly by chemists, again, Cancer Research UK supported, at Bath University and at Imperial College, have made the first inhibitor of this enzyme. There hasn't been any inhibitor up to date, but this new drug has now been tested by our group here and has been found to completely abolish the enzyme activity. And this is the drug that's in trials in patients with breast cancer whose cancers have become resistant to aromatase inhibitors.
And that was Professor Charles Coombs from Cancer Research UK at Imperial College talking about the promising role of enzyme inhibitors that alter the activity of estrogen on breast cancer.
Now, one of the important things that we can do in a hospital in order to find tumours and things, as well as doing CT scans and MRI scans, is to do ultrasound scans. And these basically use sound waves to image things beneath the surface of the skin non-invasively and harmlessly. But how do they work? Well, Ben's got Dave in a dark room to find out.
For this week's Kitchen Science, Dave has brought me into a really echoey room. Now, Dave, this is something we usually try and avoid for radio so that we sound nice and clear and there isn't an echo, a reverb on our voice. So why have you brought me here?
I thought we'd do an experiment to try and find out where the walls are, even if it was pitch black in here.
Right. Well, surely we could just fumble around and feel them.
Yeah, we could, but it's a really nice illustration of various techniques which are used in medicine.
OK, so feeling around in the dark related to medicine, this is very interesting. So what are we actually going to do, and can people try it at home?
You can try this at home. All you need is a computer, a microphone, and a piece of audio editing software. A good example is a free open source piece of software called Audacity, which you can just download off the internet.
So assuming we've got everything that we need together, what's next?
Basically just plug the microphone into the computer, set your piece of audio editing software. It has to be one where you can actually see the waveform. Set that recording and then clap your hands in the room.
Right, so we're just recording ourselves clapping?
That's right, then we're going to have a look at the waveform carefully.
OK, well, you have your laptop set up here, so go ahead, Dave. Two very different styles of clap there.
Yeah, the first one I hit the ends of my fingers together quite hard, which made a really high-pitched clap. The second one I sort of clapped together two cupped hands, which makes quite a low-pitched clap, and I thought we could compare the two.
OK, so now that we've recorded a couple of claps, we can have a look at the waveform in the audio editing software. What does this wave really represent?
Basically, it represents the pressure on your microphone. So if air is moving towards it, that's going to produce a higher pressure. If the air is moving away from the microphone, it's going to produce a lower pressure. And that's just drawn on a graph with respect to time. And you can see the two claps quite well. They make two really squiggly lines. And now we'll just zoom in and have a closer look at them.
OK, well, first of all, let's zoom in on your high-pitched clap. Now, I can see that by the looks of it, it was actually louder than the microphone could handle because the lines have gone off the top of the page. Is that normal?
If you're clapping right close to a microphone, you're going to have to turn the volume really, really low for that not to happen. But that's fine. That's what I was hoping to happen.
So we have this initial really big peak, and then we have a few sort of lumps going away from it. What do they mean?
When I clapped my hands, that caused the air to vibrate. This vibration travelled out in a wave, hit things and bounced off in what are called echoes. These came back and then vibrated the microphone. So these little extra wobbles, very short period of time afterwards. The first one is about a 200th of a second after I finished clapping my hands. And there's another one, maybe a bit more than a 100th of a second, and there's various other ones after that. And these are just the echoes coming back off the walls.
So we're actually picking up not just the first sound that we made, but also the echoes. But that, we would expect, people listening to this at home don't only hear the sound of my voice as it comes out of my mouth, but they can hear it reflecting back. They can hear that reverb. So why is this at all a surprise or even useful?
Well, it's useful because we know how fast sound travels in air. It travels at about 330 metres per second. So if you know how fast the sound is travelling, and you know how long it took for the echo to get back to you, you know how far away the thing was which it's reflecting from.
So this is how we would be able to draw the shape of this room in the dark. So going back to the very first echo, which you thought was a 200th of a second away, so 0.005 seconds after the clap, yeah?
That's right, and if sound is travelling at 330 metres per second, that means that sound has travelled about 1.5 metres to get back to the microphone.
So we know that it tells us that there is a wall or something that reflects sound 3/4 of a metre away, because it's had to travel from where we clapped next to the microphone to hit the wall and then bounce back.
That's exactly right. And there's another reflection about 100th of a second away, which is equivalent to about 3 metres of travelling. So that's probably the wall behind you, about 1.5 metres away.
And all in all, we could look at all of these different echoes in the waveform, and we can actually draw a map that would enable us to draw this room without having ever seen it.
Just like this, you don't really know what direction anything's in. To be able to work out what direction you need a really, really directional microphone. So basically, if you slowly move the microphone around the room, pointing in different directions, and kept clapping, you'd be able to work out how far away objects in that direction were and build up a picture of the room.
Then we really could use this trick to draw a map of a room, or presumably see things coming towards us. Is this essentially how radar works?
It's exactly how sonar works, which is using sound underwater, and how submarines navigate and find other submarines. It's very like how radar works, but radar uses radio waves rather than sound waves, which travel much faster and a lot further through air.
Now, earlier on, you said that we were using this as a good demonstration of something medical. What were you talking about?
I don't know if you've had an ultrasound scan. I think I probably have only had one when I was a baby and definitely can't remember it before I was born. But ultrasound basically just means sound beyond our hearing, so a higher pitch than we can hear. And to understand why you need sounds of those pitches to look inside a person, we need to have a look at the other clap, the one with cupped hands.
So we can use the same trick with sounds that we can't hear to draw a map of what's inside a person, but it has to be these ultrasound frequencies. Now, looking back at the waveform of the low-sounding clap that Dave did, we've got the same thing at the beginning, where it seems to have totally overblown the microphone, but you can't see the obvious echoes in there. You can't see the obvious higher bits in the wave that we could see in the previous one.
That's right, and most of the reason is that the sound we were using was much lower pitched. That means it's vibrating less fast, and it's got a much longer wavelength. The sound from that clap has a wavelength of probably about 0.5 metre. That means it's very hard to distinguish two reflections which are close together than about 0.5 metre, because they're just going to overlay one another, and you're going to lose all the detail in your picture.
So essentially, because it's a lower frequency, we get a much lower resolution image back.
That's right, and if you're looking inside your body, which is mostly water, that's even more of a problem, because sound doesn't travel at 330 metres per second in water, it travels at near 1 kilometre a second. So if you wouldn't be able to see it in air, you're definitely not going to be able to see any detail in your body. This means you have to use frequencies of over 1 megahertz, 1 million vibrations every second.
Well, I would never have thought that such simple kit could demonstrate how ultrasound works to see developing babies or even tumours inside people. We'll be back with another great experiment next week.
Thank you very much to Ben and Dave. And just like a very crude ultrasound scan or a short-range sonar, you can use the recordings of a hand clap to work out how far away the walls are. And just to prove to you that you can hear the echo in the recording, here is Dave's hand clap he was doing in that experiment, slowed down 16 times from its original length. So if you hear there, you'll hear the double ba-boom, which tells you that it was happening and then coming back off the wall. Here it is. So hopefully you can believe me. If you listen carefully, you'll get the two echoes there. If you want to have a go at that experiment, do let us know. We'd love to know your results. Our email address at the programme, of course, chris@thenakedscientist.com.
Keeping you abreast of the world's best science. The Naked Scientists.
This is The Naked Scientists with Chris Smith and with Kat Arney. We're talking this week about the science of cancer. Kat, got a question for you from Maggie Emerson, and she says, I've just received an email claiming that using an antiperspirant can possibly cause breast cancer. Is there any proof in this? I've been using an antiperspirant for many years.
Absolutely none. This kind of goes round and round and round on the internet. But no, there's been a lot of scientific studies done with huge thousands of women, and basically there's no difference. Using an antiperspirant will not increase your risk of cancer. Neither will having underwiring in your bra that's too tight, or any of those things that go round the internet in hoax emails.
I suppose it's a flaw in statistics, isn't it? They're saying if you look at people who use underarm deodorants, they're more likely to get cancer, but then everyone uses an underarm deodorant, so therefore by sheer fluke you're going to see people having breast cancer because it's a common disease.
But also in people who don't use underarm deodorants, you still get cases of breast cancer. I mean, the best thing is to check out something like Cancer Help UK to find out whether this stuff's actually true and try and find out.
Now, I've got a question here from Alison Dennis, who said to me, why do cancer and AIDS patients lose weight so rapidly? And actually, this is a phenomenon that's very well described. People who get malignancies very often lose dramatic amounts of weight, and people who get HIV also lose enormous amounts of weight. What they both have in common is that the immune system is often driven into overdrive, if you like. It's pushed very hard. But scientists didn't really know, aside from saying it must be some kind of production of signalling hormones in the immune system. They couldn't really tell exactly what the culprits were. But then about a couple of years ago now almost, a paper was published in Nature Medicine. It was by Heiko Jonen et al. And what they did was to find one of the factors that seems to cause this dramatic weight loss. They were using mice, and they had mice in which they implanted a prostate cancer sample, and in those mice they went on to lose dramatic amounts of weight. And when the scientists compared the levels of various chemicals in the blood of the mice with healthy mice, they found that one chemical in particular, MIC1, macrophage inhibitory cytokine 1, was at very high levels. And when they gave antibodies to that particular chemical, the mice didn't lose any weight. So it looks like it's the immune system trying to respond to the cancer or being manipulated or thwarted by the cancer, and it makes these abnormal signals that it shouldn't make, and they then cause the appetite centre in your brain's hypothalamus to go off kilter, and it causes people to lose their appetite and stop taking in the right amount of food. So they're burning off lots of energy, but they're not replacing the calories, and as a result they end up getting too thin and they lose all that dramatic amount of weight. And the fact they've identified one of these factors is really good news, because it kind of suggests that we might be able to reverse the process. Now, Cap, got another question for you. This is from David Grombach, or it might be Grombach. He says, is it possible to identify the first cell to mutate in a cancer, like the ground zero for cancer, if you will?
No, it probably isn't. Cancer cells are so mutated it would be virtually impossible to go all the way back, and in some cases the original cell may not even be there.
Oh dear, so I guess that's a bit of a no for him then. Right, OK, well let's move on with our question of the week, because this one I think we'd better, I guess, Diana, look snappy about.
Oh yes, it's a day for the puns today, isn't it? Well, I have been stripping this question down to the bone.
My name is Aaron Santos. I'm a physicist working in the chemical engineering department at the University of Michigan. And my question is this. If blood comes from bone marrow and sharks are cartilaginous fish, then where does a shark's blood come from?
Cartilaginous bones mean no bone marrow, and that means red blood cells have to be produced elsewhere.
I'm Mark Briffer from the University of Plymouth, where I'm a lecturer in marine biology. In vertebrates, a major component of the blood is the red blood cells, or erythrocytes, and these can make up to half the volume of the blood, and it's these cells that contain hemoglobin and do the job of transporting oxygen around the circulatory system. Now, in adult humans and other mammals, these red blood cells are made in the red bone marrow, and this is the soft tissue found inside the hollow bones of tetrapod, or four-limbed vertebrates, which, as well as the mammals, include amphibians, reptiles, and birds. But red bone marrow isn't the only site where red blood cells are produced, and in bony fish and cartilaginous fish that don't have bones, like sharks and rays, the main places where red blood cells are made are in the spleen and in the front section of the kidneys. And some sharks also have a unique organ called Leydig's organ, which is actually absent in the other vertebrates. And this is a large organ that's wrapped around the esophagus. And although it was discovered way back in 1857, very little is known about exactly what it does, but it's thought that it might play some additional role in producing red blood cells and also in the immune system. So although bone marrow is important for making red blood cells in humans, in fish, the most important site seems to be the spleen.
So the answer lies in the spleen of the shark, or Leydig's organ, where present. And top marks this week go to JNA on our forum, who answered it correctly.
Oh, well done. That's really good. I shouldn't sound so surprised. It's probably quite rude to sound so surprising. Yes, of course, the Naked Scientist Forum, where people can put in their thoughts on each of these questions that we publish every week. I think it's very interesting what he had to say there, because, of course, if you look at human embryology, babies, when they're developing, do a lot of their initial blood formation in the spleen and the liver and the kidney, and it's only shunted to the bone marrow later on in development, which is, I think, quite interesting, because it's almost like we're recapitulating our early ancestral origins.
So it's showing that evolutionary link, isn't it?
Indeed. There's also quite an interesting question we had. This is from Aluan, who said, where is an elephant's bone marrow? Can you please give me some more detail on elephant bones? Where do the red cells get formed in the first place? This is a really interesting question for the simple reason, when I was in Africa, I found an elephant's leg bone, and they're like a solid piece of rock. An elephant is so heavy that it needs to have almost solid rock with no solid bone with no marrow cavity in the middle, because the bones otherwise would not be strong enough to support the elephant's weight. So an elephant shunts all of its blood formation up into its pelvis, which is obviously an important place in humans too, but it means its legs are largely solid bone with virtually no marrow in them, unlike a human, where most of our blood is made in our long bones, our femurs.
Interesting. Sometimes I feel like my legs are as heavy as an elephant's. But anyway,
no comment.
Next week we have a question to make you go all square-eyed.
Hello, this is Claudia from Argentina. I have a question for you. When I was little, my parents always insisted that I keep a safety distance from the TV. Was that a urban myth, or to save me from some mysterious rays coming from the TV? And what about now? Should I insist that my son keep a safety distance from the computer screen or the TV screen? Does somebody know this? Is it harmful? Thank you very much. I love your show. Bye.
So help us answer this question of the week. You can email us, chris@thenakedscientists.com.
Thank you very much, Diana. That's Diana O'Carroll with this week's Question of the Week. You can catch up on Question of the Week through our website at nakedscientist.com. Also on the forum, nakedscientist.com/forum. So if you have any insights into why you should sit a safe distance from the TV, and not just because there's Strictly Come Dancing on it, then do send us your answers, please. You can also listen to Question of the Week as a podcast in its own right. It's on iTunes and also available from our website at nakedscientist.com/QOTW. Well, that's it for this week. Thank you very much to our guests, Karen Kirkby, John Stingle and Charles Coombs, and also our wonderful production team, Diana O'Carroll, Ben Valsler, Tom Simpkins, Mira Senthilingam and Dave Ansell. Next week, it's our Q&A show. We'll be answering all of your questions. We've got lots of them, but do send them in. chris@thenakedscientist.com if there's any scientific conundrum that you'd like us to look into for you. One other thing to bear in mind is that it's also the Podcast Awards coming up. Nominations are opening from the 4th of October, so if you like The Naked Scientists and you'd like to see us get recognised, then do please consider nominating us, podcastawards.com. Thank you for listening. It's great to have your company, and we'll see you next time.
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.